The electronic structure of atoms is what we're going to be looking at in the next several lectures. And we're going to be looking at the physical manifestations of the electronic structure, so basically what we actually see or experience, that allows us to understand atoms, which are something that we cannot see without the aid of powerful instrumentation. So the wave nature of light, and specifically observed light, has led to a better understanding of unobservable phenomena such as the electronic structure of atoms. Although we can observe those now with powerful instrumentation, our understanding of the behavior of atoms and its electronic structure has come from the observation of light. Now, observed light or visible light is a type of electromagnetic radiation. And electromagnetic radiation is basically a radiant energy that carries this energy through space or through a vacuum at a specific speed. And this specific speed is known as the speed of light, or 3.0 times 10 to the 8 meters per second. Now, there are many different types of electromagnetic radiation. Obviously, we've indicated that visible light falls into that category, but there's also radio waves, infrared, X-rays, all of these different types of electromagnetic radiation. All of these types of electromagnetic radiation, though, follow this same set of requirements. They carry energy through space at a specific speed, which is 3.0 times 10 to the 8 meters per second. Now, what's neat about all of these different forms of electromagnetic radiation is that they all have wave-like characteristics. So basically, they follow this rule in terms of their speed of travel in a vacuum, and they also have a specific set of physical characteristics. So they basically have this wave-type function in terms of their specific pattern of travel. Now, we look at these waves, and we've decided to basically create characteristic or defining features. The wavelength is characterized as the distance between two peaks or two troughs. So the wavelength of your specific electromagnetic radiation is related to basically the spacing between either these peaks or two troughs. Frequency, on the other hand, is basically the number of waves that pass a specific point in 1 second. So we would count the number of waves that pass a specific point in order to establish our frequency. Now, both wavelength and frequency utilize a different set of variables. The wavelength value here is known as lambda, and I kind of think of it as a squiggly wave. It kind of looks like a wave, so it's a wavelength. Frequency here is represented by the symbol nu, which is kind of looks like a V, but it's not V. Please make sure that you're differentiating between frequency and something like velocity. So now that we've defined the wavelength and the frequency, we can actually talk specifically about what the differences are amongst these different types of electromagnetic radiation. Now, remember, they're all electromagnetic radiation. They all have wave-like characteristics, but obviously we know that visible light and X-rays behave very differently when they interact with our bodies. So we can talk about those details now that we understand these characteristics of the light wave. So we have a nice diagram here that allows us to establish the differences between the different types of electromagnetic radiation. Now, we already mentioned that they all behave the same way in terms of their speed when traveling through a vacuum, and that they all have wave-like properties. So, how are these different from one another? Well, the differences lie in both the wavelength and frequency. So, if you notice here, all of the different types of electromagnetic radiation that we'll typically talk about are represented on this graph. So normally, notice we have radio frequency, microwaves, infrared, the visible spectrum, ultraviolet, X-rays, gamma rays, right? Okay, so all of these types of electromagnetic radiation are types that we could discuss. Now, notice we have wavelength up here across the top, notice that the values of wavelength that are corresponding below are increasing as we go to the right. So, radio frequency waves have the longest wavelength of the group that we see here. Gamma rays have the shortest wavelength. In that same way, notice that the frequency of radio waves is going to be much smaller than, say, the frequency of gamma rays. So, what differentiates, a radio wave from something in the visible spectrum? Well, you can look at it with respect to wavelength, or you can look at it with respect to frequency. Basically, we can differentiate the different types of electromagnetic radiation based on the physical characteristics of their individual waves, so their wavelength and their frequency. So, we take this data or this information and this understanding into our next slide. So we've established that both frequency and wavelength are what differentiate the different types of electromagnetic radiation. Now, we've also established that all of the electromagnetic radiation types all travel at the same speed in a vacuum. Now, obviously, we can take this relationship between our frequency and our wavelength, and we can relate it to the fact that our speed of light is what all the electromagnetic radiation types adhere to in that vacuum state. So we get this equation right here when we interrelate our speed of light and our wavelength and frequency. And we saw on the other previous slide that when we had very large wavelengths, our frequency was very slow or very low. When we had very small wavelengths, our frequency was very high, right? So we know that our frequency and our wavelength are inversely proportional. So basically, as one gets larger, the other gets smaller. Now, this equation here is going to allow us to find out some information based on observable phenomena. So, we might be able to figure out the frequency, we might be able to figure out the wavelength of some type of electromagnetic radiation. If we know one of those, if we know wavelength or we know frequency, we can subsequently figure out the other variable. So, if I know wavelength, I can find frequency. If I know frequency, I can find wavelength. So let's go ahead and let's look at the variables that are being expressed here in this equation. So we know that c is the speed of light. That's the variable that we use there. Speed of light is usually expressed as 3.0 times 10 to the 8 meters per second. Obviously, the units can be different, but make sure that you're paying attention to this type of thing whenever you're doing calculations. Wavelength, obviously wavelength is a distance from trough to trough or from peak to peak. So there's going to be a unit of distance or length corresponding to our wavelength measurement. So meters, nanometers, centimeters. It'll be important for you, especially between meters and nanometers, to be able to utilize the conversion factor between those two. Frequency, right here, frequency as represented by the letter nu, or the variable nu, can be represented or is represented by hertz. Now, the unit of hertz, guys, can be represented in several different ways, and I want you to understand that they all mean the exact same thing. You need to make sure you put this into your head so that whichever way the frequency is given with respect to its units, you can convert and not feel uncomfortable. So hertz is actually a representation of inverse seconds, so 1 over s, okay, so 1 over seconds. This can also be written as s to the minus 1. All three of these things mean the exact same thing, and they are all units of frequency associated with this new value. So make sure that you're paying attention to your units. And let's go ahead and look at a little bit better diagramming of this inverse relationship that we see between frequency and wavelength. So if we go ahead and we look at these waves here, I want you to actually visualize how this inverse relationship between your frequency and wavelength actually exhibits itself. Okay, so if we look at this first wave here, obviously we have a fairly long wavelength, right? Okay, we have peak to peak. That's the wavelength of this specific wave. Now, if we go to this next example here, notice that our wavelength is a little bit shorter, right? Peak to peak is shorter than what we saw in this original situation. If we look at this third one, notice that the wavelength is even shorter. Now, wavelength and frequency, remember, are all inversely proportional. So as one gets bigger, the other is going to end up being smaller. So if we go ahead and we look at the relationship between wavelength and frequency, we should see an inverse relationship. So this first example here obviously had the largest wavelength, so the frequency here of the three should be the smallest. So let's see if that's the case. Okay, so we have this wavelength that's long, we have a frequency of 3 hertz. We have a shorter wavelength here, now our frequency has increased. We look at an even smaller wavelength, our frequency has become even even larger. So what do we see here? We see an inverse relationship between our frequency and our wavelength. If we have a high frequency, we're going to have a small wavelength. If we have a small frequency, we're going to have a large wavelength. So this is our inherent understanding. Now, also remember that when we're looking at our frequency, we're actually counting the waves that pass a certain point in a specific amount of time, so that 1 second. So when we're measuring our 3 hertz, our 6 hertz, our 12 hertz, remember that's, how many waves have passed per second. So in this case 3, in this case 6, and in this case 12 over that second measurement time. Okay, so now that we understand the parts of a wave and that we've visualized the actual inverse relationship between frequency and wavelength, let's go ahead and let's utilize this equation to help us find out some information about specific examples of electromagnetic radiation. So we have a couple of examples here, and they both ask us to calculate a couple of different things. So in this first question, they're asking us, what is the wavelength of light with a frequency of 5.89 times 10 to the 5th hertz? Okay, so in this specific situation, or this specific example, they have given us our frequency. They've given us our new value, and they've told us it's 5.89 times 10 to the 5th hertz. Okay, remember hertz can also be represented as inverse seconds, so 1 over s. Okay, and they want us to solve for our wavelength, so they want us to solve for our lambda. Now, frequency and wavelength are related by the equation that we just looked at, so lambda times nu. And we also know c, because c is our constant of 3.0 times 10 to the 8th meters per second. Okay, so we have 2 of the 3 variables we need in order to calculate this type of problem. Now, before we start plugging numbers in, we always want to check if our units are appropriate. So notice I have meters per second and I have hertz. Okay, so remember guys, hertz is the same thing. Okay, hertz means 1 over s, the number of waves that pass per second, right? Okay, so the units here could also be written as 1 over s. So if I look at this specific example here, I have seconds down at the bottom, seconds down at the bottom here, meters. There's no opposite, or there's no relationship with meters here, so I think that we're on the right path. Okay, so if we go ahead and we solve for the variable that we want in this equation, which in this case is going to be wavelength, we're going to end up with c divided by nu. Okay, so it's going to be the speed of light divided by our frequency. So lambda is going to be equal to 3.0 times 10 to the 8th meters per second. Okay, we're going to divide that by our frequency, 5.89 times 10 to the 5th inverse seconds, or hertz, either way. Okay, and if we go ahead and plug that into our calculator, this will give us 5.09 times 10 to the second. Okay, and then if we check our units, seconds and seconds are going to cancel, and meters are going to be left over. So we have 5.09 times 10 to the second meters as our wavelength. Okay, the units make sense because wavelength is obviously a measurement of the length, the distance between those peaks and peaks, or troughs and troughs, however you want to measure it. So basically, we've utilized this equation to calculate our wavelength by solving for the variable that's appropriate, as seen here, making sure our units match here and here, and obviously plugging the numbers in correctly to our calculator. Okay, so we can also use this type of equation to solve for frequency, and that's what's being asked for in our next problem. So in the problem below, they say, what is the frequency of a blue light with a wavelength of 484 nanometers? So they have provided us with our wavelength of 484 nanometers. They have told us that they want us to solve for frequency. Okay, so that's our unknown, that's the variable we're solving for. Okay, and we know that we can relate both frequency and wavelength by the equation that we used in the previous example. So we know that our speed of light is equal to our wavelength times our frequency. Okay, so now that we know that we're using that equation, we're of course going to write out our variable, which is our speed of light that we do know. Okay, so meters per second. All right, so we have all the variables that we need. Let's go ahead and solve for the one that we do not know. Okay, so we're going to manipulate this equation. Okay, our new value, our frequency, is going to equal speed of light divided by our wavelength. Now, before we plug anything in, as always, we need to make sure that our units are appropriate. So I have meters per second here in terms of our speed of light. And I have my wavelength. However, my wavelength here has been given in nanometers. Nanometers and meters will not cancel each other out when I plug it into the equation over here. So I need to convert one of these two in order to make it match. So for simplicity's sake, I'm going to convert the 484 nanometers into meters. Okay, so 484 nanometers. Okay, now what is the relationship between nanometers and meters? Okay, well, there are 10 to the 9th nanometers for every 1 meter. Okay, so this is the relationship that you should expect. Okay, so when I take my 484 nanometers and I divide it by 10 to the negative 9, this gives me 4.84 times 10 to the negative 7th. My units, nanometers cancel, so meters is what's left over. Okay, so my wavelength has now been converted from nanometers into meters, and it is equal to 4.84 times 10 to the negative 7 meters. So I can now take these numbers and plug them in and not have to worry about problems with the cancellation of units. So frequency is going to be equal to 3.0 times 10 to the 8th meters per second. Okay, so that's my speed of light up top. And I plug in my new wavelength value in meters, so 4.84 times 10 to the negative 7th. Okay, and my meters are the units there. Okay, and when I go ahead and plug this into my calculator, this is going to give me 6.20 times 10 to the 14th. Okay, and my units, the meters and meters are going to cancel, and I'm going to be left with inverse seconds, or you could express this as hertz. So my frequency is equal to this value and has these appropriate units. Okay, so the C equals lambda times new equation that we've learned about today allows us to basically take known information about specific electromagnetic radiation types and subsequently calculate one of the other features that we are not measuring, such as frequency or wavelength. So we can we know frequency, so we can measure or calculate our wavelength. We know wavelength, so we can calculate our frequency. And this relationship will be tied directly to other theories that we're going to approach as we continue through this lecture series. Now, there are some limitations to the wave model that we've just been discussing in terms of the behavior of light. And the reality of it is there's specific behaviors that are not able to be explained with the simple equation and simple explanation that we've talked about in this lecture so far. So the three things that we're going to be discussing and in future lectures is the emission of light from hot objects, otherwise known as black body radiation. We're going to explain that and look at the basically work that was done by scientists to explain this phenomena. Same thing with the emission of electrons from metal surfaces. Basically this photoelectric effect, we're going to explain that and look at that. And then we're going to look at the emission of light from excited gas atoms. So basically the production of emission spectra. And the understanding of all of these phenomena is what has really solidified our understanding of basically the electronic structure and features of atoms. And the amazing thing about these experiments is this basic idea or this basic understanding that we just talked about in this lecture was expanded upon by some of the greatest minds that have existed on our planet. So we'll go ahead and take a look at those in our next few lectures.